Hello, everyone. My name is Tayana Etienne. I am professor at the State University of Haiti, and I am the co-founder of Solutions. Solutions is a software company with a focus on public health, e-governance, agriculture sectors. I am the I.E.E.E. Puerto Rico and Caribbean Community Communication Society Chair. I've always been passionate about the impact of proper data infrastructure and management practices to empower communities and organizations. And I am glad to find plenty of resonance with my own areas of interest and many great topics that I am discovering on our I.E.E.E. Communication Society platform. In this regard, I am very glad to welcome our distinguished professor, Dr. Lynn Kai, for the webinar Self-Evolving and Transformative Protocol Architecture for SysJ. Dr. Lee is a professor. Yes, hello, Dr. Lee. Dr. Lee is a professor from the University of Victoria. She's currently research in this area of communication and networking, network protocol and architecture design, supporting emerging design, multimedia traffic, and also the Internet of Things. Dr. Lin is also a recipient grant in 2020, in 2010, in 2015 from the Natural Science and Emerging Research Council. And she's also have been nominated with Networking and Networking Workman Star in Computer Networking and Communications. Dr. Kai is an active member of I.E.E.E. She co-founded and chair the I.E.E.E. Victoria section, Vehicular Technology and Communications. And she's an elected member of the I.E.E.E. Vehicular Technology Society branch of the Board of the Governors, from Board of Governors. She's the Associate Editor-in-Chief of I.E.E.E. Transactions of Vehicular Technology. And she's also a distinguished lecturer for the I.E.E.E. VTS Society and for I.E.E.E. Communication Society. Welcome, Dr. Lin.
Thank you so much. Thank you. Can you help me to share the screen for my PPT? Thank you, Diana, for your nice introduction. And it's my great pleasure to be here. I really feel very exciting because this is the first time I have the chance to talk to your chapter. And today I will talk about self-evolving and transformative protocol architecture for 6G. Next page. We know that 5G has been commercialized since 2020. Yeah, yeah, I can change the slides now. Thank you. Yeah. So we know that each generation, wireless technology generation, lasts about 10 years, a decade. So now is the pivotal time to work on fundamental research issues for 6G. Particularly, we need to take a look of what's the good opportunities and the big challenges for 6G network and protocol architecture design. We know that from 1G to 5G, our current 5G has already been able to cover 4G, 5G, or cellular system has already a good coverage of high populated areas. However, the high populated areas only occupy a small percentage of Earth's surfaces. So the percentage of our Earth's surfaces being covered by the current cellular system and the internet is only about 66%. Okay, so 6G is anticipated to become a ubiquitous system covering all lands, include those rural, remote island, and the depopulated zone. Particularly like in our Earth, we know our Earth is more looks like a water planet. 70% of our Earth's surfaces are water or oceans. So 6G is anticipated to extend the coverage to above or under water. And the 6G will also try to investigate the altitude domain. So in addition to the ground communication, we will incorporate things like UAV, drones, balloon, as well as all kinds of satellite, LEO satellite, MEO satellite, and GEO satellite to have this coverage from space, air, to even deep space. So 6G is quite ubiquitous in coverage. And to support this kind of ubiquitous coverage, we needed to use all kinds of wireless communication technologies and spectrums, from sonar, microwave, millimeter wave, to higher frequency terahertz laser. So all these different wireless spectrums and associated technology have quite different physical medium and technologies. We needed to incorporate them. This is a big challenge for our networking. And also, because we have all kinds of new things to be incorporated in 6G for ubiquitous coverage, such as UAV, AUV, satellite, we will see many, many new different types of mobility. So in 1G to 5G cellular system, we only see the mobile user. So when we talk about mobility, we talk about user mobility. But in 6G, because of these AUV, UAV satellites, the whole access network and even the backbone network will move. So we needed to handle not only user mobility, but also network mobility. So we can see there's a lot of new challenge to incorporate different types of wireless spectrums, wireless links, and handle both user mobility and the network mobility. So how to adapt our network to these different types of communication technology and links, as well as mobilities, is a big challenge. Next, from applications perspective, our 6G system will support real-time applications such that they can interact between human, cyber systems, and physical systems. And these new applications have many new stringent quality of service requirements in different dimensions. For instance, our AR, VR, hologram communications, or distributed learning requires much higher data rate. And for our human to machine, human to algorithm communications, or machine-to-machine, algorithm-to-algorithm communication like distributed learning, they also require very high reliability and very stringent on-time and in-time service. Sometimes the delay and the jitter can only be in millisecond or even below millisecond level. Our TCP/IP protocol for internet was mainly designed for human communications. Our humans are very intelligent, so we can tolerate some loss, we can tolerate some delay. So like voice over IP can lose 10% of packets and our human can still understand the communication. But for those algorithms, those machines, those robots, they are less intelligent than our humans. They are very sensitive to those packet loss and delay. So our TCP/IP protocol stack was not able to handle all these stringent loss, delay, reliability requirements. So this is another big challenge. And for this human cyber system and the physical system interaction, we can see that in 6G, there are many new communication modes. So currently, we mainly have this unicast or point-to-point communication modes. But in 6G, we will see things like from point one sender to multiple receivers. So this is a kind of broadcast and multicast communication modes. Or from multiple transmitter to one receiver, this kind of in-cast communication mode. Or from multiple sender receiver to exchange information within the group, we call the group cast communication modes. So here we use a wildcard star to represent all kinds of multicast, broadcast, in-cast, group cast. Okay. We know that our TCP/IP protocols was designed mainly for unicast, point-to-point communication. When we have all kinds of starcasts, the current protocol stack is extremely low efficient, particularly consider those communications is over our wireless medium, which has the broadcast nature. So how to deal with this starcast requirement and leverage the broadcast nature of wireless medium is a big challenge. And finally, our 6G system is anticipated to be intelligent. We all know this fast development in AI machine learning technology. And we anticipate that in 6G, we are not only build a data pipeline like today's internet, we deliver bits only. And in 6G, in addition to this data exchange, we anticipate the network can incorporate communication capability with sensing, storage, computing functions, become a very large scale distributed system supporting ubiquitous intelligence. So this is our vision. So in other words, our 6G systems can using advanced sensing and signal processing to collect data, using multi-layer caching and content distribution to store data, using sophisticated coding and compression technology to process the data, and using advanced AI machine learning technology for network management and control. And more importantly, our 6G network can support many new emerging centralized or distributed learning and AI applications. So this is our final goal for 6G, which is a really challenge for today's internet. If we take a look of today's internet architecture, we know that the internet protocol stack have so-called hourglass kind of feature. In the top, we have many different application layer protocol to handle different applications requirements. In the bottom, we have many different physics link layer technologies to deal with different types of link mediums. And in the middle, we only have very limited choices, a handful transport layer protocol, TCP, UDP stuff, and then the IP protocol in the network layer to deal with all types of communication requirements, applications, and scenarios. Okay, so when we have new applications come, new quality of service requirement come, new network scenario come, so what we have to do is develop new protocols, or we need to use some tunneling over tunneling technology to address those challenges. And we see that this kind of solution is really inefficient. For instance, in the top, TCP/IP have no capability to guarantee end-to-end delay or end-to-end throughput jitter, so no end-to-end service guarantee. And in the link layer and the transport layer, we have seen both layer have many redundant functions. So this link layer retransmission and transport layer retransmission, for instance, they may conflict with each other. So this is particularly undesirable in the situation of a wireless domain. We heavily rely on link layer retransmission to handle that. Okay, and also this kind of tunnel over tunnel solution will introduce extremely high overhead, and this is particularly undesirable for new application like ultra reliable low latency services and the massive machine type of communications. So our internet protocol architecture is inadequate to address all these challenges. And then we can take a look of the 5G domain. Now let's take a look of 5G architecture, because 5G is more recent compared to the internet architecture. And the 5G architecture in the 5G core, it takes an approach called CUPS. The mobile core is divided into the control plane and the user plane. So this is the architecture called the control and the user plane separation, or CUPS. This is quite similar to software-defined network architecture proposed and deployed in today's data center. And with this CUP architecture, the control signaling traffic, including user authentication, registration, mobility tracking, those will be supported using the protocol of SCTP over IP and go through these mobile core networks. And then for the users' data, like the cell phones, audio, video, multimedia traffic, text, etc., they will go through the data plane using the GPRS tunneling protocol, GTP protocol plus UDP over IP to deliver. So this is what happened in 5G. And with this kind of CUPS architecture, we can see that those control functions and the management functions, such as the access mobility management, session management, so all those functions could be developed as a software and implemented in the cloud. So we can move all these things into the cloud in mobile core. And then the user data goes through UPF, goes through the internet. So this is the idea of this 5G architecture. So with this kind of software-defined control management, the deployment of this control function and the management function are quite flexible, could be quite efficient, and can be deployed in the cloud at relatively low cost. However, we find that in 5G, there is still something missing. So for those high reliability and low latency services, 5G missed the capability of very fast control to ensure fast reaction to service requirement and the network dynamics, particularly in sub-second level, because all those clouds are far away from the network. The propagation delay takes hundreds of milliseconds or even seconds. So this is the physical limitation we cannot breach. So by push all the intelligence into cloud, this is insufficient to handle what is the biggest challenge in 6G. We need to guarantee delay and the throughput and the reliability in millisecond level. Okay, so in order to do such kind of fast control, we find that it's impossible to shift all these control functions into the cloud. So we need to have fast reaction inside our network. So all those fast control in millisecond level should be associated with each data packet, with each data flow. It has to rely on the communication protocols and in the user data plane. So this is our vision. In conclusion, to deal with these 6G challenges, we need a new protocol architecture. Here, we call this self-evolving and transformative protocol architecture. In this architecture, we hope this each protocol can be assembled, compiled, configured in real time using a wide range of control functions according to different applications' quality of service requirements. So it can handle those starcast service modes, support ubiquitous coverage in different dynamic environment. So this new architecture can essentially help this 6G become an essential infrastructure for future ubiquitous intelligence. To achieve that, we think that on top of 5G CUPS architecture, we need to go one step further. So we need to divide the control plane into different levels according to the control data scale. Okay, so sorry, go back. To the right, the figure, the yellow block, these are the user control. These are the control associated with user billing, accounting, etc. These things can be taken care of in second or multiple second level. So we can push that into the cloud, like what we did in 5G. And in the middle green part is our session level control. Deal with session level authentication, policy ruling, mobility management. So these need to be done in tens or 100 millisecond level. So this can either be pushed to cloud or can be implemented in edge servers. And to the left side, the blue one, this is the new thing we introduced here. So we found that we need to have some protocol control agent to deal with flow and packet level control. Okay, so these protocol control agents are just a piece of code or software that reside in each network entity, routers, and systems, intermediate systems. Okay, so with this protocol control agent in each router, each intermediate systems, so we can let the network entities become more intelligent. So we using this protocol control agent to enable this in-network intelligence. Okay. So with this in-network intelligence, we can see this 6G will work like this. Here we use this yellow bar to represent user control functions. So user control functions can be pushed into the cloud, and the green bars are the session control functions. So the session control functions can also be in the cloud or in edge server if needed. And then the blue bar will represent both the data plane and the data plane associated protocol control agent. So this agent is everywhere in every router, every end systems. Okay. Then next, given this new architecture, we need to think about how we can develop what we call the self-evolving and the transformative protocols to handle all those challenges for those new applications and the new scenarios, new coverage. Okay. So our idea is instead of using this one fit all approach like the IP protocol, fit all applications without much concern on the applications, and not those one-on-one approach to develop one new protocol for one new applications, and then when we have anything new come, we need to develop more and more. So instead of these two approaches, our new protocol architecture should allow our protocol to be able to serve a large number of applications while consider their needs. So we have one protocol, but this protocol can be very flexibly compiled and configured to handle different service requirements and different network dynamics. So the key here is to take the modularity approach. This is very similar to our large-scale software development or like the operating systems and so forth. So we've already seen this modularity being happen in many other computer science domains. But here we just want to use this idea to be incorporated in our network protocol architecture. Okay, so with this modularity, what we need to do is we try to decompose the protocol control functions so that we take this kind of Lego approach. So when we decompose the protocol into different Lego blocks, and then we can at any time take any blocks and compile a new protocol, compile the protocol to satisfy the new requirements and new environments. Okay, so here is an example of protocol function decomposition. We have transport layer protocol, for instance, TCP usually need to deal with connection management, flow control, error control, congestion control. So for each function, it need to take a few different procedures. And for these procedures, we can actually use different protocol mechanism to realize them, right? So we can use TCP like handshake-based connection management, or we can use timer-based connection management. For flow control, we can use like TCP window-based flow control, or we can use some other solution like rate-based control. Or error control wise, we can use ARQ type error control or FEC type error control or hybrid one. For congestion control, we can use loss-based or delay-based or etc. etc. So here we can see like for this example, when we decompose this transport layer protocol into 4 functions, and each function gets, say, 3 choices using choice 1, choice 2, or disable both of them, like 3 choices, then we can have 3 times 3 times 3 times 3, 81 different solutions for this transport layer protocol. Okay, so we can see that if we have more choices for each functions, and if we have more functions, the possibility can grow exponentially. So with this modularity and the decomposition, actually we can help our protocol to deal with a very large amount of different requirements and network dynamics. So here, once we have this control block being decomposed, so in network entity, we need to rely on this protocol control agent. This is just a piece of code to do this reassemble. So what it do is it can take the input of application service requirements as well as transport networks service measurement, network measurement, and the low physical link layers measurement, mobility prediction, location, images sensing, all this information. And then from its function libraries, this is what we have already decomposed, to pick up the right function to compose them, to assemble them. Of course, during this procedure, it can rely on very advanced or sophisticated or simple and efficient AI and machine learning technologies. Okay. So we can see that this protocol control agent is very intelligent. It needed to deal with protocol configuration and adaptation according to service requirements and according to network measurement and the network environment. So essentially, it makes the decision needed to make the decision in real time to help this protocol control agent to make decision faster. We can propel a kind of a menu, a set of default configuration for easy start. Okay, so it can easily start with some known protocols, and then by keeps on monitoring the network environment and keeps on monitoring the service requirement, it can change this configuration in real time So take the action. Essentially, this is a real-time multi-arm banded problem. And there are many existing tools, advanced learning tools to handle these multi-arm banded problems, such as contextual banded reinforcement learning, or even large language model using transformers, so on and so forth. Okay. So I think this is the part that require a lot of research efforts over the years. So we really call for input and a call for more research efforts from the research community to think about how we can develop a nice protocol control agent that can make sensitive decisions or optimize their decisions. Okay. So let me quickly summarize this new protocol architecture feature. So here, the main difference is this new protocol architecture, we rely on in-network agent uh, or in-network intelligence. So this protocol control agent need to be deployed inside our network entity. This is different from the cloud idea of push all the intelligence into cloud. Here we want to introduce those intelligence back to the network. And the reason is with this protocol control agent, we can take information not limited to those traditional layered architecture. So this protocol control agent can collaborate with each other, make intelligent decisions for end-to-end service support, particularly delay, jitter, and throughput. This distributed in-network intelligence can react to our channel network application mobility environments much faster and more robust and more efficiently. This new architecture will let this protocol control agent to choose control functions from the growing function library, make our protocols self-evolving. So we can anticipate that in the future, we probably do not need to develop a new protocol, but we really need to develop a new control function. So the protocol can take new functions to be more efficient and effective. And our protocol control agent can switch functions from a single flow when the service requirements or the environment change. The protocol can switch, for instance, at the beginning, probably only have one pair of sender and receiver exchange information. And over the time, there may be new users coming, new devices coming, they need to exchange information. So we can evolve from a unicast session to a multicast or in-cast or group cast session. So the protocols could be transformative in this dynamic environment. That's why we call this new protocol architecture self-evolving and transformative architecture. We also want to highlight that if in today's internet, majority of the device is not intelligent, it's just a TCP/IP. This new protocol architecture can also backward compatible with TCP/IP. Say if the protocol control agent notice the rest of the network can only support a very limited functions, so they just go back to use as these limited protocols to talk. And whenever it finds other nodes can understand the new protocol, etc., then they can switch to new functions, so on and so forth. So we anticipate this set protocol architecture can be deployed incrementally, which is very important for network protocol design and development. And in our lab, we have applied this new protocol architecture to deal with a few issues. For instance, we develop new routing solutions to support this packet level delay guarantee. So in each flow, even different packets have different delay requirement. Some probably require a 25 millisecond delay, the other require 50 millisecond delay. We don't care. The routers can, based on this delay requirement of individual packet, to route the packet through appropriate paths to guarantee that delay requirement. So this is one outcome I'm quite happy with. I don't have the time to go through the detail. I will give the link to the papers that develop this packet level delay guarantee, the routing. And we also have this Starcast with QoS support. For instance, in vehicle to everything communication system, vehicles need to share this extended sensing information and in real time. So this is like a Starcast service with very stringent delay requirement. And I will also give a link to another recent paper handle this situation. And today I will more focus on this user case, mobility management using multi-path handoff in satellite system. I will give a few slides to discuss this. And in our lab, we also try to use the new architecture to see how we can integrate sensing, computing, storage, and the communication service for 6G. So this is still ongoing research issues. So here I want to use a few minutes to introduce a case study of how our new protocol architecture can deal with mobility in satellite networks. So we know that for mobility support, one promising technology is called multi-homing. Basically, each devices will associate with multiple network interface, and each interface have its own associated IP address. So with this multi-interface, we can maintain a connection between this mobile device with multiple access points simultaneously, such that during movement, even some of the link between the mobile device and some AP is disconnected, the other link can still work, can still maintain the service. So this multi-homing is a very nice solution for support mobility. It also can be applied to support network mobility. Okay. And if we take a look of the existing mobility management solution, for instance, in cellular system, in the link layer, we have seen this multi-link solution, such that the base station can multiple base station can maintain multiple link to a cell phone and to support a soft handover for this cell phone. But this multi-link solution cannot support the handover in heterogeneous network or the network being controlled by multiple ISPs. And this link layer solution somehow conflict with the end-to-end congestion control. So it does not really work very well to support multimedia services. And then the multi-homing transport layer protocol design, as I mentioned, is more desirable. So this is the reason that in our research, we also try to focus on the multi-homing solution. And in terms of multi-homing, we need to take a look of what kind of transport layer protocol can support multi-homing. One thing is a multipath TCP, but we found that TCP protocol is inherently insufficient to deal with satellite communication compared to a newer transport layer protocol, QUIC. We found that the QUIC can achieve zero round-trip time handshake, and the QUIC use connection ID instead of IP to maintain the connection. And if we do anything in QUIC, we only need to change in the user domain, not the kernel change. So that's why in our work, we focus on using QUIC protocol, but instead of the traditional QUIC, which can only maintain one connection, one path, we develop a multi-path QUIC protocol. And with our set network architecture, our multi-path QUIC protocol can take the input from the link layer and the transport layer together using these multiple input, multiple data to make more intelligent decision in terms of how to schedule the packets into different interface, how to adapt the congestion window of different paths, so on and so forth. Okay, in NS3, Network Simulator level version 3, we have implemented our decomposed multipath QUIC protocol, and we also incorporate these mobility-aware functions. And then we test its performance when we use this multipath QUIC protocol to handle this communication in satellite network, which have this network mobility because the access network is from satellite. The satellite keeps on moving. Okay. So because of our mobility aware multicast protocol can take can take more information in different layers, so it can do some proactive reaction to achieve more smooth or seamless handover and a more accurate congestion control. So this is simulation results in NS3. So we compare our proposed Quick, which is the red one, with the existing Quick protocol, MP Quick OLIA, as well as the TCP protocol with more advanced congestion control BBR. We found that our solution can always outperform the others. This is because we are more intelligent to understand what's going on in the physical link layer and the mobility situation, so we can do much more accurate decision. Okay, so given the time, I want to conclude here. In this talk, I highlight a self-evolving and transformative protocol architecture, which has been proposed to address 6G challenges. So how we can let the network entities have this distributed control function to coordinate with each other for end-to-end service support, particularly delay, jitter, throughput support, and how and this new protocol architecture can handle those user-centric spectrum and mobility management, like I just mentioned, and it can be used to support Starcast and the ubiquitous intelligence down the road. Okay, so there are actually many open issues with this new protocol architecture, and I really uh, encourage other researchers to take a look, to think about how can we decompose the whole protocol stack and make new control functions, how this control agent can effectively discover network environment and frequently explore the options to map the QoS requirements and the network dynamics to control policies effectively, efficiently, and optimized. So this is really a big problem that will require for lots of ongoing research efforts. And then how this distributed intelligent agent can leverage advanced AI or machine learning technology to enhance network security, data privacy. So all these are open issues for this new protocol architecture. Okay. And here I list a few papers. Some of them introduced the use case I mentioned. And the first one is the magazine paper introduced this protocol architecture for 6G in great details. So if you're interested, you can go through these papers. With that, I want to conclude my talk and thank you for your attention. And if there's any question, I will be happy to answer. And if you have future questions, feel free to contact me through my email address here. Yeah, this is the end of my talk. Thank you.
Thank you. Thank you so much, Dr. Kaye, for this great presentation. And thank you for sharing so valuable and interesting information about the design principles and so let's say, protocol architecture for 6G. Thank you so much. It's such a great presentation. I think that we have two questions. From I don't know if you can see the chat on yes, thank you, Abigail.
Okay.
We have the first question.
Yeah, I see the first question. Let me read it. What type of information data points you foresee to be required to analyze in order to provide the network with sufficient intelligence to be able to control itself as well as to evolve? Yeah, very good question. Right now I can see that because we need to our network is always to support applications and leverage all types of communication technologies. So the protocol control agent really need is the applications requirement, service requirement, as well as the network measurement data. So these are the data input to this protocol control agent. And then based on this data, the protocol control agent can find the suitable protocol configurations such that it can match using the limited or varying like network resources to support the upper layer applications demand. And in this process, I think things could be quite dynamic. For instance, at the beginning, I can begin with some default setting. For instance, I just use, say, TCP to support application. And then later on, if we find that the network is actually quite clean and the packet loss or delay is very low. In this case, I probably can decouple the error control from my transport layer because it only slow down my transmission and there is not much useness. So in that case, we can use less costly solutions and more efficiently to deal with the service requirement. Or on the other hand, if the network becomes really bad, so even the existing TCP cannot handle that, probably we need to add on some error control, end-to-end error control, forward error control, or network coding, etc. So this is how it works. Okay. And the second question is, are there any privacy concerns that have surfaced during this case study phase regarding the collection of training data to be used for training the AIs that will monitor controls? Excellent point. So at this point, when we do this research we didn't really put the data privacy concern into consideration, and we agree this is a very important issue. So in the end, the user and the network needed to negotiate what levels of data that the user is willing to release to the network. This is similar to our cell phones app, right? So many apps can provide a good service only if the user is willing to share certain types of information to the app owner. So in the future, we believe there will be some negotiating like process between the user and the net. So if the user really need certain types of services and the user may need to compromise some of its data and information to facilitate those services. Okay.
Okay.
I see another two questions. How will set protocol architecture for 6G impact the satellite communications? And this is a is exactly what we are really interested in. So in our lab, we have acquired a few Starlink dishes because we found that in the future, satellite networks will be an important part of our 6G network. And in addition to the several like Starlink dishes we have, we also collaborate globally. We have our partners in the east coast of US and Canada and the south of US and the in the island in the middle of Pacific Ocean, so things like that. So we try to use this global test bed to acquire lots of data information about the satellite communication systems. And in my slides, if you take a look of my slides, there is a paper uh, published which we try to use this global test bed to first of all understand the existing network structure of Starlink. So I think our paper probably is one of the most comprehensive one to like reverse engineer what's going on in Starlink. And during this procedure, we also notice many issues that current Starlink is not fully efficient. For instance, the routing protocol in the inter-satellite communication for Starlink is quite preliminary and quite unoptimized. So we believe that our new protocol architecture, particularly instead of using IP address for routing decision, we in satellite network, because of the satellites have such a regular structure, so satellite will always follow some orbit, and there are fixed number of orbits for the satellite network. Given the regularity of the satellite architecture, we found that it's no sense to use the IP protocol, IP address for routing. We should be able to leverage other like orbit or like even the location information, it will be better to do this routing, etc. And this is feasible if our routing protocol is more flexible instead of based on the IP address to do the routing decision. We can use other information to do the routing decision and make the routing much more efficiently. So this is how we figure, how we vision our set architecture can impact the satellite. Yeah. Is cybersecurity considered in 6G? Okay, yeah, good question. Cybersecurity is always a very important issue. Of course, there are many researchers focus on cybersecurity in 6G. And for me, I'm more a network protocol person. So I want to at the beginning focus on the network protocol design, and then once our protocols are there, we can investigate what's the consequence for in terms of privacy and security. And in my opinion, in the future, because each network entities are more intelligent, so the whole network society becomes more intelligent. So this actually can help to say identify the bad guys and to make the network even more secure than today. So just imagine a society with lots of dummy person, then any intelligent hacker can easily hack through the system. But if a society full of intelligent person, so the hackers will have difficulties to hack through because you have many more places to monitor, many more places to coordinate and to identify troubles or bad situations. So that's my opinion. Yeah. Thanks for the questions.
Okay.
Yeah.
Thank you so much, Dr. Kai. I have a question.
Sure.
Yes, we know that some applications like remote health care can really need to have high speed and reliable connectivity. I wonder, how do you see the potential impact of 6G on mobility area protocols on those kind of applications?
Yes. Yeah. Sorry, I probably missed a few sentences. Let me rephrase. So you want to
I
ask the
want,
question?
yes, I want to know your talk about the potential impact, on application with the remote application or remote healthcare application. This
Mhm.
kind of application
Right.
needs high speed
Mhm.
connectivity and reliable connectivity. How
Yeah.
6G can have a potential impact, positive impact in those applications.
Definitely, definitely. Yeah. Yeah. First of all, like with 6G, we anticipate we can leverage many different types of wireless technologies to support a much higher data rate. So we can like leverage not only microwave but also millimeter wave or even terahertz. So so in that cases, particularly in short distance, we can achieve much higher data rate to acquire the information to support those kind of application really needs a high data rate. And in addition to that, like what I said, the multipass is an opportunity that we can leverage multiple access points, multiple spectrums to maintain the connectivity between the devices and the network such that even though some of the um, spectrum is in like is congested or in some bad situation, you can still using other passes or other access links to maintain that reliability and the low latency. So I think one thing is so this 6G set architecture can help to leverage more access links, the leverage more heterogeneous links to support those applications, have a truly high demand in terms of throughput, delay, jitter, and the loss. So I think that's a good opportunity. And then if you are talking about those applications where users are in remote area, the
Yeah.
current internet coverage cannot access, then we can see that leverage satellite,
Yeah.
sometimes balloon, UAV, etc., can help to improve the coverage. Even the people is in remote area without a good infrastructure. Like in Canada, we have these First Nation communities in those remote area where the internet is not available at all. But then now we can bring the Starlink dish to those community to help to connect them with the rest of the world. So I believe 6G will have very high impact, not only in those highly populated areas, but more importantly, those unpopulated and underserved places.
That's great. Thank
Yeah,
you. That's great. Another question is,
I see two other questions. Is there
yes.
a possibility for a future in which different configuration of the Starcast can live within the network and that can communicate between themselves? Yes, this is what I believe possible. So how to make it possible, I think it's not only my job, but also many people's job. So I really encourage people to think about it. So I really see the opportunity here. Sometimes we will have the service between multiple users, and this number of users join and leaving will be a dynamic situation. So we will see the evolving of unicast to suddenly change to multicast, or sometimes change to groupcast, and then can come back to group unicast in some situation. So I think this is a very interesting research topic, and I hope someone, probably some of my team members, probably some other researchers can address that. Yeah.
Yes.
Yeah. I also another question: is there a possibility? Yeah. So yeah, this is the
Listen. Yes.
question. Good.
Yes, my last question is
Yeah.
about policy. And I would like to know what do you think in the context of CJ? Do you think that we have a good chance to reach global compatibility, interoperability with the 6J ecosystem? You have presented in your you have talked in your presentation about some issues. What is the bigger challenge that you think that we have regarding this
Yeah.
architecture?
Yeah, I really appreciate this question. Yeah, definitely a big challenge if we want to push a new protocol architecture in the internet. I think what I'm trying to promote here is we come up with this new solution, but at the beginning, probably just a small domain of the network can take that, like inside the data center, or for satellite network, which is somewhat separated from the rest of network. In some small domain, we just take it as a trial, and we can see the benefit. And eventually we can hope, oh, because this is a better solution, people are convinced to switch
Yeah.
their network. And hopefully this new thing can keeps on growing and can take over. And inside the internet, I never can claim any new technology is good enough to convince the network to converge to a new thing overnight. So my idea is we make sure this can be incrementally deployed, and at the beginning we just try to deploy it in a specific domain, like inside a manufacturer, for instance, or inside a certain like a vehicle network communication system, things like that.
Great, great. Thank you so much, Dr. Kai, for this great presentation. We really appreciate your insight about this subject. Thank you so much.
Thank you for having me, and thanks for all the audience and all the questions.